Close your eyes for a moment and try to imagine the oldest light in the universe. It began its journey 13,800,000,000 years ago, when the cosmos was young, hot, opaque, still cooling from the Big Bang. This light, called cosmic microwave background radiation, permeates all of space, a luminous whisper from the birth of the universe. But here's something that defies intuition. The universe itself measures much more than 13.8 billion light years. Why? Because space didn't remain still while this light traveled. It expanded, stretched, grew. And this expansion is not uniform. It's not simple. The space between distant galaxies is constantly stretching, making them appear to be moving away from us at increasing speeds. The farther away a galaxy is, the faster it seems to move away. Not because the galaxies are moving through space, but because the space between us and them is itself expanding, like dots drawn on an inflating balloon. And this increasing exodus has revealed something extraordinary and disconcerting. There is a mysterious force accelerating this expansion. Scientists call it dark energy, not because it is black or gloomy, but because it is completely invisible, undetectable, except for its repulsive gravitational effects. It is dark in the sense of being unknown, enigmatic. And here's something that should make you pause in humility. Dark energy accounts for about 68% of everything that exists in the universe. More than 2/3 of reality is composed of something we don't know what it's made of. We can measure its effects, mathematically model its behavior, but its fundamental nature remains one of the greatest mysteries of modern science. The rest of the universe, the 32% that is not dark energy, is largely composed of another invisible substance, dark matter. It emits no light, absorbs no light, and reflects no light. It is completely transparent to all forms of electromagnetic radiation that we know of. And yet, we know it exists because we can see its gravitational effects. Galaxies spin faster than they should based on visible matter alone. Clusters of galaxies are held together by gravity that cannot be explained solely by the stars we see. Without dark matter, galaxies like the Milky Way would simply fall apart. The stars in the outer regions spin so fast that, without additional invisible mass providing extra gravity, they would be flung into intergalactic space. Dark matter is the invisible gravitational glue that holds galactic structures together. And the Milky Way is not static, frozen in its current form. It is in motion, evolving, and in a few billion years, it will undergo a dramatic transformation. It is slowly colliding with the Andromeda Galaxy, our large spiral neighbor located about 5 million light-years away. The two galaxies are approaching each other at about 110 kilometers per second. This collision will create a galactic giant that some astronomers have affectionately nicknamed Lactomeda, a merger of the Milky Way and Andromeda. In approximately 4 billion years, the two galaxies will begin to interpenetrate, their spiral shapes gravitationally distorting, and stars being redistributed into chaotic orbits. But here's something reassuring. Even during this dramatic galactic merger, individual stars will hardly collide with each other. The space between stars is so immense, light years of emptiness between each point of light, that billions of stars can pass by each other without any physical collision. It's a gravitational dance, not a physical shock. However, the gas clouds inside galaxies are another story. They will collide, compressing against each other, creating shock waves and regions of high density. And when gas is gravitationally compressed, it heats up, collapses, and eventually ignites nuclear fusion. It will be a storm of star formation, millions of new stars being born in a relatively short period. A cosmic baby boom triggered by the collision. These new stars will be born from matter that has already been reused countless times throughout cosmic history. Atoms are not easily destroyed. They persist, changing places, incorporated into stars, ejected in supernovas, floating in interstellar clouds, then incorporated again into new stars and planets. It's cosmic recycling on a galactic scale. And the atoms in your body, every carbon in your DNA, every calcium in your bones, every iron in your blood, were once in ancient stars that exploded millions or billions of years ago. These catastrophic explosions are called supernovas, and they are events so energetic that for brief moments they can surpass the brightness of entire galaxies. Supernova scatter heavy elements throughout the cosmos. Gold, silver, platinum, uranium, all elements heavier than iron, are forged primarily in supernovae, or in collisions of neutron stars. These elements are launched into space at significant fractions of the speed of light, enriching the interstellar medium. And without these explosions, rocky planets like Earth simply wouldn't exist. First-generation stars, born soon after the Big Bang, were composed almost entirely of hydrogen and helium. There was no carbon to form organic molecules, no silicon to form rocks, no iron for planetary cores. All of that was created in subsequent stars and spread by supernovae. The dust left behind by these explosions travels for thousands, even millions of years, floating through interstellar space until it eventually encounters new star-forming regions. Cold, dense molecular clouds where gravity is beginning to pull matter together again. In these regions, gravity slowly compresses dust and gas, creating concentrations that begin to rotate. As they collapse, they conserve angular momentum, spinning faster and faster, flattening into disks, the planetary nurseries where new stars are born in the center and planets form in the surrounding regions. These protoplanetary disks contain trillions of particles, microscopic dust grains, chunks of ice, rocky fragments. Over millions of years, these particles slowly collide, adhering to one another through electrostatic forces and weak gravity, gradually growing from grains to pebbles, from pebbles to boulders, from boulders to planetesimals, objects kilometers in diameter. But not all of these planetesimals end up forming planets. Many are ejected from their systems through close gravitational encounters with giant planets, launched on trajectories that take them into interstellar space. They become interstellar objects, homeless cosmic wanderers. Some of these objects travel for millions or even billions of years through the void between stars until, by sheer chance, their galactic orbits lead them to cross paths with another star system, perhaps our own. When we detect interstellar objects like Oumuamua, Borisov, or 3I Atlas, we are not just seeing space rocks. We are witnessing literal fragments of other worlds, pieces of the cosmic history of other suns, silent messengers from planetary systems we will never visit. Each one is precious beyond measure, each one a window into planetary formation processes around other stars, each one a tangible connection to the vastness of the galaxy that surrounds us. Breathe slowly. Feel yourself part of this cosmic tapestry, woven from recycled atoms, invisible energy, and connections that span billions of years. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a supercluster of galaxies spanning over 10 billion light-years. To put that into perspective, it's so gigantic that it challenges the very cosmological idea that the universe should be uniform on sufficiently large scales. Structures like that shouldn't exist, but they do, defying our expectations. And here's something mind-boggling. This structure is so enormous that light takes longer to cross it than the universe has taken to expand from the Big Bang to the present. It's an apparent temporal contradiction, a puzzle that scientists are still trying to fully solve. How can something be larger, in a sense, than the age of the universe itself? It's a question of geometry, expansion, and what exactly we mean by size. Superstructures like this may have formed from microscopic fluctuations in energy shortly after the Big Bang. Imagine quantum vibrations the size of atoms, tiny irregularities in the density of matter and energy, being amplified by cosmic expansion until they become galactic walls stretching for billions of light years. That's scale multiplied through deep time. These primordial fluctuations are a direct consequence of cosmic inflation, an event that occurred in the first moments after the Big Bang when the universe grew exponentially, expanding faster than the speed of light. Not because anything was moving faster than light through space, but because space itself was stretching at extraordinary rates. And inflation left scars, permanent imprints in the cosmic microwave background radiation, that ancient light from when the universe first became transparent. They are tiny, hot and cold spots scattered across the sky, invisible to the naked eye but detectable by sensitive instruments. They are fingerprints of the birth of the cosmos, fossilized patterns of amplified quantum fluctuations. This cosmic microwave background radiation has a remarkably uniform temperature of 720 Kelvin, just a few degrees above absolute zero. But oscillations of millionths of a degree reveal intricate patterns from the early universe. They are clues about initial conditions, about the density of matter in different regions, about processes that shaped everything that would come after. These small temperature variations correspond to regions where matter density was slightly higher or lower, and these minute differences determined where the first galaxies would emerge. Denser regions had slightly stronger gravity, pulling in surrounding matter, eventually collapsing into stellar nurseries. It was gravitational destiny written in primordial quantum fluctuations, and the first stars born from these dense regions were monsters. Called Population 3 because they are the first generation before Populations 2 and I that came later, some were so enormous that they had 300 times the mass of the Sun. They were nuclear furnaces of incomprehensible scale, burning their fuel voraciously and lasting only a few million years before exploding catastrophically. When these first supernovas detonated, they enriched the early universe, until then composed almost entirely of hydrogen and helium, with heavy elements. Gold, iron, carbon, oxygen, nitrogen, the entire periodic table above helium was forged in stellar furnaces and scattered by explosions. The raw materials of rocky planets, oceans, organic molecules, and ourselves. Without those first stellar generations, planets like Earth could not exist. There would be no silicon for rocks, no iron for planetary cores, no oxygen for water, no liquid water, no complex chemistry, no life. We are made of the ashes of stars that died billions of years ago. Over time, primordial galaxies, small, irregular, chaotic, weighed each other down to form giant galaxies like the Milky Way. The universe organized itself hierarchically, like cosmic Lego pieces fitting together, larger structures emerging from the merging of smaller ones. And this process continues. The Milky Way is constantly colliding with small dwarf galaxies that orbit around it. It swallows one of these satellite galaxies every few billion years, incorporating its stars and redistributing its matter. Evidence of this can be found in stellar streams, long, curved trails of stars ripped from these smaller galaxies by the Milky Way's gravity. They look like bright rivers crossing the night sky, visible on detailed star maps. They are galactic ghosts, the stretched remnants of worlds that were once independent. One of the most prominent is the Sagittarius Belt, remnants of a dwarf galaxy that is being devoured by the Milky Way right now, at this very moment. Its stars are being silently incorporated into the larger stellar population of our galaxy. It's galactic cannibalism, a slow but inexorable process. And at the heart of the Milky Way, hidden by dense clouds of dust and gas, lies an immense gravitational presence. Sagittarius A, a supermassive black hole with more than 4 million solar masses compressed into a region smaller than the orbit of Mercury. Despite its colossal size, Sagittarius A is relatively calm right now. It's not actively devouring large amounts of matter, but energetic markers around the galaxy, giant bubbles of X-rays and gamma rays, show that it has experienced violent explosions in the past, episodes of frenzied feeding when it swallowed stars and clouds of gas. These outbursts may have shaped the rate of star formation in the Milky Way. When the black hole wakes up and begins actively consuming matter, the released energy can blow gas out of the galactic core, disrupting star formation. Or, paradoxically, the shock waves can compress gas in other regions, accelerating star birth. It's a complex, two-way influence. Around Sagittarius A, there is a cluster of ultra-fast stars called S-stars. Some travel at more than 8,000 kilometers per second, dizzying speeds, trapped in tight orbits by the extreme gravity of the black hole. Observing these stars is like watching particles in a natural gravitational accelerator, and these orbits allow us to test Einstein's general relativity in regimes impossible to replicate on Earth. As stars pass close to the black hole, space-time curves so drastically that relativistic effects become enormous. And so far, in every test, Einstein has won. His predictions are confirmed with extraordinary precision. But some subtle movements of these stars suggest the possible presence of dark matter concentrated in the galactic center. Small orbital anomalies that can be explained by invisible mass distributions. What connects this local mystery to the greatest cosmic enigma? The fact that 95% of the universe is composed of matter and energy that we do not understand. Dark matter and dark energy. The dominant components of a reality that remains, for the most part, hidden from us. Let your breathing slow down. Feel the vastness of these scales, from quantum fluctuations to galaxy walls, from first stars to black holes. Relax deeply. More cosmic connections await. Most of the universe is invisible. 95% of everything that exists is composed of dark matter and dark energy. Mysterious forces that shape the structure and destiny of all reality. Only 5% of the universe is made of normal matter that we can see, touch, and directly measure. We live as a tiny minority in a cosmos dominated by forces we barely understand. Dark matter acts as an invisible gravitational glue, holding entire galaxies together. Without it, stars in the outer regions of galaxies, spinning at high orbital speeds, would fly away, scattering into intergalactic space. The gravity of visible matter alone is not enough to keep them bound. But dark matter, distributed in immense halos around and through galaxies, provides the necessary additional gravitational mass. Dark energy, on the other hand, does the exact opposite. Instead of pulling, it pushes. It acts as a negative pressure permeating all of space, accelerating the expansion of the universe. The more the universe expands, the more dark energy emerges, because it is linked to the very volume of space, creating a feedback loop that makes the expansion accelerate even further. And this accelerated expansion points to a bleak future. The universe is becoming increasingly cold, dark, and silent. Distant galaxies are moving away so fast that they will eventually disappear beyond our observable horizons. In trillions of years, future civilizations, if they exist, will look at dark skies where only a few local galaxies will be visible, the rest having been swept beyond the reach of light. But when the universe was young, everything was the opposite. It was small, hot, dense, so dense that light could not travel more than minuscule fractions of a millimeter before being absorbed and re-emitted by free electrons. It was an opaque plasma, a cosmos of shimmering haze where visibility was essentially zero. Only 380,000 years after the Big Bang did the universe cool enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, light was free to move without hindrance. This moment is called recombination, and the light released at that instant is what we see today as cosmic microwave background radiation, an echo of the birth of the universe, visible in every corner of the sky. This radiation is not perfectly uniform. Detailed maps of it show small dents, temperature variations of only millionths of a degree. But these tiny irregularities were gravitational seeds. Slightly denser regions had slightly stronger gravity, pulling in surrounding matter, growing over billions of years until they became galaxies and clusters of galaxies. And between these clusters, there are giant voids, regions of space so enormous and empty that they could contain thousands of galaxies, but contain practically nothing. They are cosmic deserts on a scale difficult to imagine. The largest of these is the Boötes void, a cosmic chasm 330 million light-years wide. If you could stand in the center of this void, looking in any direction, you would see almost complete darkness. No visible galaxies, just black emptiness occasionally dotted by a solitary, lost galaxy. But even these voids are not entirely empty. There are traces of extremely rarefied hydrogen, just a few atoms per cubic meter, densities that are vacuum better than anything we can create in a laboratory. But on cosmic scales, this tenuous hydrogen forms filaments, part of the cosmic fabric. This hydrogen is part of a gigantic cosmic web that connects all the galaxies in the universe. Imagine a three-dimensional sponge with dense filaments of matter connecting nodes where galaxies are concentrated, and immense voids between the filaments. This is the large-scale structure of the universe, not uniform but textured, with patterns reminiscent of neural networks or cosmic spiderwebs. This web functions like invisible highways through which matter and energy have flowed for billions of years. Gas flows along the filaments, being gravitationally channeled towards the nodes, fueling galaxy formation at the intersections. At the intersections of this web, galaxies emerge, like droplets forming where multiple rivers meet. Matter accumulated in gravitational knots, collapses, forms stars, and eventually complex galactic structures emerge. And at the center of almost all of these galaxies lies a supermassive black hole. Concentrations of mass so dense that not even light can escape. These gravitational giants shape the behavior of the stars around them, regulating star formation, sometimes accelerating it, other times halting the birth of new stars through energy released when they devour matter. But black holes don't indiscriminately suck everything in like cosmic vacuum cleaners. Many of them, when actively fed, launch collimated jets of energy and matter that travel millions of light years, traversing entire galaxies and emerging into the intergalactic medium. These jets can seed future star-forming regions, spreading heavy elements, carbon, oxygen, iron, gold, throughout the cosmos. They act as cosmic fertilizers, enriching regions that would otherwise be composed only of primordial hydrogen and helium. And these heavy elements only exist thanks to giant stars that died explosively as supernovas. Every atom of carbon, oxygen, nitrogen, iron in the universe was forged in stellar furnaces and scattered by catastrophic explosions. There was no carbon in the Big Bang, no oxygen, no building blocks of complex molecules. This means something profound. All living matter, you, me, every creature that has ever existed on Earth, was born inside stars that no longer exist. We are literally made of star ash, recycled cosmic dust, atoms that were once part of burning suns billions of years ago. Thus, every atom in your body is a recycled piece of the universe, traveling for ages through the cosmos, incorporated into stars, ejected in explosions, floating in interstellar clouds, eventually incorporated into the solar nebula that formed our system, condensing on Earth, absorbed by organisms, passing through countless generations of life, until now forming a conscious being capable of contemplating the cosmos itself and recognizing its stellar origin. You are not merely in the universe. You are the universe, a temporary form that cosmic matter has assumed, capable of reflecting upon itself, of asking questions about origins and destinies, of feeling awe at the vastness from which it emerged. Feel this connection. Each breath contains oxygen forged in stars. Each heartbeat moves iron from ancient supernovas. Continue breathing gently. The cosmic tapestry continues to unfold. The universe may seem empty when we look at the space between the stars, but quantum reality tells a different story. Every cubic centimeter of space, even in the most perfect vacuum, contains constantly bubbling quantum energies. Pairs of virtual particles appear and disappear in infinitesimal fractions of a second. Fluctuations allowed by quantum mechanics as long as they exist only momentarily. This energy is called vacuum energy, and it may play a key role in the accelerated expansion of the cosmos. It is one of the most promising candidates for explaining the nature of dark energy, that mysterious force that dominates the universe. Some physicists believe that this quantum vacuum energy is the microscopic manifestation of dark energy, responsible for tearing galaxies apart at an ever-increasing rate. If true, it would represent an extraordinary connection between the smallest, quantum fluctuations, and the largest, the fate of the entire universe. Dark energy accounts for about 68% of everything that exists in the cosmos. More than all the stars, planets, gas, dust and black holes combined. It is the dominant component of reality, and yet it remains profoundly mysterious. Nobody knows exactly what it is. We can't see it directly. We can't touch it. We can't detect it in a laboratory. We only perceive its gravitational effects on a cosmic scale, the acceleration of the universe's expansion, the way large-scale structures evolve. It's like trying to understand the wind by only observing how trees move, without ever feeling the breeze directly. Dark matter makes up about 27% of the universe, acting as that invisible glue that profoundly influences the formation and evolution of galaxies. Without it, galaxies would spin so fast that they would fall apart. Stars in the outer regions would be launched into intergalactic space like drops of water from a tornado without a sufficient gravitational center to hold them together. The Milky Way, for example, appears to float within a vast halo of dark matter, a diffuse spherical distribution that extends far beyond the visible galaxy itself, perhaps 10 or even 20 times larger than the stellar disk we see. It's as if the visible galaxy were only the emerged part of a much larger gravitational iceberg. This invisible halo profoundly affects even the trajectory of stars orbiting far from the galactic center. Observations of the orbital velocities of stars in the outer regions of the Milky Way reveal that they are moving faster than they should based solely on visible mass. This is indirect but compelling evidence of the presence of additional invisible mass, dark matter. And the influence of dark matter goes beyond individual galaxies. It also shapes the formation of galaxy clusters, gigantic structures that bring together hundreds, sometimes thousands, of gravitationally bound galaxies. The mass of these clusters is dominated by dark matter, not by the stars we see. These clusters are not randomly distributed throughout space. They are connected to each other by invisible filaments, the cosmic web we mentioned earlier. This web is like a skeleton of the universe, trillions of light-years of filaments of dark matter and gas along which galaxies are arranged like pearls on a necklace. Between the filaments lies the cosmic void, almost completely deserted regions where galaxies are extremely rare. Some of these voids are so large that they could contain hundreds of Milky Ways and still appear essentially empty, cosmic deserts on an incomprehensible scale. However, even in these seemingly barren voids, dark matter and dark energy exist, influencing the structure and evolution of space. Nothing is truly empty in the universe, only differently filled. The distribution of the cosmic web that we see today reveals something fascinating about the universe's past. It had an initial phase of cosmic acoustics, when pressure waves rolled through the primordial plasma in the first hundreds of thousands of years after the Big Bang. These were literal sound waves traveling through the young cosmos, compressing and expanding matter in regular patterns. These waves left permanent marks on the distribution of galaxies we see today, known as baryon acoustic oscillations. They are statistical patterns in the separation between galaxies, a preferred distance that reflects the size of sound waves in the early universe. The patterns of these oscillations are like a cosmic ruler, helping scientists measure the rate of expansion of the universe at different epochs. By comparing real distances with apparent distances, we can reconstruct how the universe expanded over billions of years. But here's a profound problem. This expansion rate, when measured by different methods, doesn't match. Observations of the local universe, using supernovae and other standard candles, give one value. Observations of the cosmic microwave background radiation, light from the primordial universe, give a slightly different value. The discrepancy is small but statistically significant, and it has been growing as measurements improve. This is the biggest crisis in modern cosmology, known as the Hubble tension. The Hubble constant, which measures how fast the universe is expanding, should have the same value regardless of how we measure it. But it doesn't. It's as if the young universe and the current universe are telling slightly different stories about the rate of expansion. Some scientists believe this could indicate new physical laws. Perhaps dark energy isn't constant, but changes over time. Perhaps there are additional energy components we don't yet know about. Perhaps our understanding of gravity on cosmological scales needs adjustments. It's a crisis that could revolutionize fundamental physics, or it could be a subtle systemic error we haven't yet identified. But the tension persists, growing as data improves, and scientists around the world are working intensely to resolve it, whether by discovering new physics or identifying errors in measurements. In any case, something profound is being revealed about the nature of the cosmos. Imagine the universe as a complex symphony played on instruments we can barely see, governed by laws we are still learning. Right now, as you lie comfortably, something extraordinary is happening around you, something you cannot see, hear, or feel, but which is fundamentally transforming the very fabric of space. With each passing second, the universe expands a little more. And not only that, this expansion is accelerating, as if an invisible and mysterious force were pulling everything outward, stretching the very fabric of reality, as if inflating a cosmic balloon that never stops growing. Think about this for a moment. Right now, the space between distant galaxies is expanding, not because they are moving through space, but because space itself is expanding, creating more distance where there was less before. It's as if new pages are constantly being inserted into the book of the cosmos, pushing everything further away. But what is causing this accelerated expansion? This mysterious force has an appropriately enigmatic name: dark energy. And here's something that should make you pause and reflect. This invisible substance makes up about 68% of everything that exists in the universe. Think about that. Almost 70% of all reality is made of something we can barely begin to comprehend. And the truly frustrating part for scientists is that despite dominating the universe, dark energy cannot be directly detected. No instrument we have can capture or measure it. We know it exists only through its effects on cosmic expansion, in the same way that you can infer the presence of wind by seeing trees bending, even without being able to see the air moving. It is one of the greatest mysteries of modern physics, a ghostly presence that permeates everything but escapes our direct observation. But dark energy has an equally mysterious counterpart: dark matter. This enigmatic substance makes up about 27% of the universe, and, like its energetic cousin, it is also completely invisible to our instruments. It emits no light, absorbs no light, and reflects no light. For all practical purposes in the electromagnetic spectrum, it simply isn't there. So, how do we know it exists? Dark matter is detected only by the gravity it exerts on things we can see. It literally pulls galaxies together, holding everything together with its invisible gravitational embrace. Astronomers noticed something strange decades ago. Galaxies were spinning too fast. Given the amount of visible matter they contained, they should have been tearing apart due to centrifugal force, their stars flying into space like water from a garden sprinkler. But they don't fall apart. Why? because there's something else there, something we can't see, holding everything together. Without dark matter, galaxies would spin so fast they would simply disintegrate like cosmic fireworks, their stars scattering into the void in all directions. But the extra gravity of dark matter acts like an invisible glue, keeping everything in place. And the more scientists studied this phenomenon, the more extraordinary it became. Detailed observations show that giant halos of dark matter envelop entire galaxies, forming a kind of invisible skeleton. Every galaxy you can see is actually embedded within a much larger sphere of dark matter, like a pearl inside an invisible shell. These halos are often 10 times larger than the galaxies they enclose themselves. But the story doesn't end with individual galaxies. These massive halos of dark matter connect galaxies to one another across empty space, forming long structures known as cosmic filaments. Imagine gigantic threads of invisible matter, stretching hundreds of millions of light years across the cosmos, linking groups of galaxies like beads on a cosmic necklace. And when you broaden the perspective even further, when you look at the large-scale structure of the universe, something truly impressive is revealed. The filaments intertwine like enormous webs, creating what astronomers call the cosmic web. It is the largest structure in existence in the universe, a pattern of filaments, knots, and voids that stretches across billions of light years in every direction. This web is so gigantic that it defies our capacity for comprehension. Its nodes, the points where multiple filaments meet, are not individual stars or even galaxies. They are entire galaxies and superclusters, structures containing thousands or even millions of galaxies, each with billions of stars. It is an architecture of such vast scale that it makes our minds stumble when trying to visualize it. And within the largest of these cosmic knots, we find places like the Virgo cluster, a massive concentration of over 1,000 galaxies bound together by gravity. And where is our own Milky Way in this grand structure? Occupying a humble position on the periphery, like a small town on the outskirts of a gigantic metropolis. We are not the center. We are not special in terms of location. We are just one among thousands. But even Virgo, impressive as it is just a tiny speck in an even larger structure, the Laniakea supercluster. The name comes from Hawaiian and means immeasurable heaven, a profoundly fitting name for a region encompassing over 100,000 galaxies. Imagine that. 100,000 galaxies, each with hundreds of billions of stars, all forming part of a single coherent structure. And all these galaxies in Laniakea share something in common. They are all being pulled toward a mysterious central point. Astronomers call it the Great Attractor, and the name is as ominous as it is fitting. This object or region is so massive that it warps space-time around it significantly, and its immense gravity drags thousands of galaxies toward it, like leaves being pulled into a whirlpool. We, along with our galaxy and everything in Laniakea, are hurtling toward the Great Attractor at a speed of about 600 kilometers per second. It's a journey that began billions of years ago and will continue for billions of years into the future. But here's the most impressive and frustrating thing. We can't see it clearly. Why? Because it lies behind the bright band of the Milky Way, in the region that astronomers call the zone of avoidance, where the dust and stars of our own galaxy block our view of what lies beyond. It's like trying to see through a dense forest. We know something is there. We can measure its effects, feel its gravitational presence, but we can't see it directly. It's one of the great frustrations of modern astronomy, knowing that something immense and important exists right there, but not being able to observe it clearly. So, what is the great attractor? Some theories suggest it may be an extreme concentration of dark matter, a region where the invisible substance has accumulated in extraordinary quantities, creating a deep gravitational well that pulls everything around it. It would be like a particularly dense knot in the cosmic web, a focal point of intense gravity. But other theories suggest something even more intriguing. Perhaps the great attractor is only part of something even larger, a structure called the Shapley supercluster. Located beyond the great attractor, Shapley is the most massive known supercluster in the local universe, containing more than 8,000 galaxies in a region spanning millions of light years. It is so massive that some astronomers believe it may be the Shapley supercluster, and not the great attractor, that is actually pulling all these galaxies together. And here's where the story gets truly dizzying. Even Shapley may be just a piece of something unimaginably vaster, structures on such large scales that we still haven't been able to fully map them. Every time we think we understand the structure of the universe, we discover that it extends even further, is even more complex than we imagined. All of this shows us a profound and somewhat humbling truth. Most of the cosmos is dominated by invisible forces and structures. Dark energy pulling everything together. Dark matter holding everything together. Structures of unimaginable scale connecting billions of galaxies in patterns we are barely beginning to comprehend. And what do we see? Those tiny points of light in the night sky. Those telescopes pointed into deep space capturing images of distant galaxies. All of that is just a small fraction of the true architecture of the universe. It's like seeing only the lights of a city at night, but not being able to see the buildings, the streets, the infrastructure that truly supports everything. We live in a universe that is, for the most part, invisible to us. Only about 5% of everything that exists is ordinary matter, the kind of matter that makes up stars, planets, and you. The other 95%, mystery, dark energy, dark matter, forces and structures that we can barely detect, much less understand. It's a lesson in cosmic humility. We think we understand the universe because we can see stars and galaxies, because we can measure and calculate and predict. But we are, in fact, blind to most of reality. It's as if we were living in a world where we could only see a small band of the electromagnetic spectrum, and all the true complexity of reality existed in wavelengths that our eyes simply cannot detect. And perhaps that's comforting in a strange way. It means there's so much more to discover, so much more to learn. Every answer we find reveals 10 new questions. Every mystery we unravel shows that there are even greater mysteries waiting. So while you rest now, consider this. You are floating on a small rock, orbiting an ordinary star in an average galaxy on the periphery of a supercluster, all being slowly pulled through space by invisible forces we barely understand. In a universe dominated by substances we cannot see, connected by a cosmic web of unimaginable dimensions. And yet, here you are, ordinary matter organized in such a complex way that you've gained the capacity to contemplate all of this, to marvel at its vastness and mystery. It's simultaneously humbling and profoundly inspiring. The universe is bigger, stranger, and more wonderful than any of us can fully imagine. And as you drift off to sleep, know that you are part of this great cosmic tapestry, connected to everything through unseen forces, moving through space on journeys that began billions of years ago and will continue for billions more. Good evening, Cosmic Explorer. May your dreams be as vast as the invisible universe, and as profound as the mysteries that still await discovery.